Before we start, let's look at what we covered in lecture number 6. So in lecture number 6, we were studying this generic question in the spatial degree of freedom as to how to quantify the correlation in between the field vibrations at two separate space points rho 1z, rho 2z, and the way to do that is to pick up some field from rho 1z, some field from rho 2z, combine them at some other point rho z, and then by studying the intensity at this point, one can then study the correlation between the fields at these two space points. Now in that context, we looked at some essential mathematical concepts first, and the first one was the spatial stationarity. So just like temporal stationarity, spatial stationarity means that if a field is spatially stationary, it means that the correlation functions of all the orders are independent of the space origin, but usually we mean it in the sense of wide sense stationary, in which case it is just the mean and the second order correlation function that has to be independent of the space origin. So for wide sense stationarity, we saw that we have to have that the intensity should be independent of the space origin, meaning intensity at rho should be same as intensity at the origin. So intensity should be space independent. And for the correlation function, we saw that the wide sense stationarity constraint translates to the fact that the cross-spectral density function, the correlation function, depends on the spatial coordinates only through their difference. So this W function, the correlation function, has to have a dependence on the space coordinate only through the difference delta rho. We then also looked at the angular spectrum representation of fields going in the positive z direction. This is very similar to what we did in the time domain when we looked at the frequency domain representation of a time domain signal. But when we are discussing the angular spectrum representation, it is just a little different. In the time domain signal, we have this VR to the time domain signal. We just take its Fourier transform, and this V tilde R omega, that is the frequency domain signal. In fact, for studying this spatial correlation, we'll only be studying this quantity V tilde R omega, which we actually call U rho z. Since this is at a single frequency, we then don't show this frequency, just call it U rho z. Now in the case of time, we just take this Fourier transform time to frequency, but in the case of space is a three-dimensional vector, but that we represent that as a rho, which is two-dimensional vector, and z, and then we just take the Fourier transform of this rho. So it's not a three-dimensional Fourier transform, it's just a two-dimensional Fourier transform that we are after. So that is the difference between how we handle time domain signal versus the space domain signal. And the reason for doing this only two-dimensional transformation is that we are mostly interested in, at least in this course, the beam-like solution, the beam-like field solution that are going in the positive z direction. So for that purpose, we looked at this kind of representation, and if we saw that there are several constraints that this U tilde QZ has to follow because of our constraint of having a beam-like solution, propagating solution, and propagating in the positive z direction. We saw that this U, because of all this constraint on U tilde QZ, the solution that it can have is of this form, U x y z. This we have written in the Cartesian coordinate system. So U x y z is a q x q y e to the I q x x q y y plus this w z. And just to remind, here this k that we are using here, the mod of that k is this is the k is the wave vector, and then mod of that k is related to the frequency through omega equal to ck, and this k is a three-dimensional vector. We write that as qx q by w, which is what we have it here. This qx qy form a two-dimensional spatial frequency vector, and of course this z component, and the mod of q, we write that as this non-bolded q. Okay, now we see that this is actually not a Fourier transform, but if we look at this field at z equal to 0, then this is a perfect Fourier transform. Ux by 0 is a qx qy e to the I qxx qyy dqx dqy. So that's a perfect Fourier transform, and this way we can actually go from the xy degree of freedom to this qx qy space. Now we can invert this and write a qx qy in terms of uxy0. So these two form perfect Fourier transform pair, and that's two-dimensional space and then two-dimensional spatial frequency basis, which form the Fourier pair. Okay, now coming back to this field, we saw that since we are mostly interested in the beam-like solution, one very good approximation, or one very often encountered approximation, is what's called paraxial approximation, and that happens when this q, this spatial frequency vector, this q is much smaller than k. So when q is much smaller than k, then we saw that we can actually write this u in this form, that it is the ikz is aq, it is the iq dot rho, it is the iq squared 2k z d2q. So that's that. This is the form of u for the paraxial approximation, but this is the form of u in the most general case. Okay, so this is what we did in lecture number 6, and today we are going to now quantify and study how to quantify the spatial correlation that we started to kind of study with this kind of interferometer, which is also known as Young's double-slit interferometer. So as we saw last time, we are interested in finding studying the correlation between the field vibrations at this location and this location, and the way to do, and this is the generic methodology, the way to do is just pick up the field, some field from here, and then combine them here. So the field at rho z, which is what we are representing, a u rho z, is k1 u rho 1 0, that is a field from this point, k2 u rho 2 0, that is a field from that point. And then t1 is the time it takes for the field to go from this point to that point, t2 is the time it takes from for the field to go from this point to that point, and that's why this e to the I omega t1, e to the I omega t2, they are showing up here as the amplitudes. Now once we have the amplitude, then we look at the intensity at rho z, and which is given by u star rho z, u rho z ensemble average, and this we have did it in the last lecture as well. So this is simply sum of this 3 terms, in fact 4 terms. This is complex conjugate here. So first term is basically the intensity u star rho 1 u rho 1, intensity at this point, and there is this geometric factor k1, and that's because of the size of the slit and the direction and all that. There is the second term contains the intensity coming from this location, u star rho 2 u rho 2, and again some geometric factor. And the third and the fourth term, these are the interference terms, and they contain this correlation term u star rho 1 u rho 2, and this is the quantity we are after. And so in fact only when this term is present we see interference fringes, the very familiar Young's double-slit interference fringes, and that is actually just because of the presence of this term. So we will look at now as to how to quantify this quantity u star rho 1 u rho 2. So now we can actually write this in terms of just the intensities or the spectral densities. So this is just this term is just the S at rho, this term is k1 square S rho 1 S rho 2, and the interference term with this cross spectral density W rho 1 rho 2 Z. And the point is that by looking at the intensity at this detection point, we should be able to figure out something or something about this function W rho 1 rho 2 Z. And this is exactly how we quantified correlation in the temporal domain as well. So this is the very generic methodology that is used in interferometers. Okay, so we can just simplify this in exactly the same manner as we did for time. So here we substitute k1 star k2, this quantity, as k1 mod k2 mod e to the I phi k, and we write this cross spectral density function W rho 1 rho 2 Z, this as this quantity, which is just simply multiplying it in the numerator and denominator by S rho 1 S rho 2. This is S rho 1, and this quantity we recognize, we defined it last time. This is the degree of spatial coherence. So mu rho 1 rho 2. This is in general a complex quantity. So we can also write this as its mod and its argument. So S rho 1 S rho 2 under root this modulus of mu rho 1 rho 2, the degree of coherence, and this argument. Now if you substitute this form for W and this for k1 star k2, then we obtain that the intensity is given by this k1 first term, second term, and then this term where we have a cosine term. So this cosine term, which has this omega t2 minus t1, the temporal information as well, and these arguments of mu and phi k. So when any of these things change that's what gives us the Young's fringes that we actually, Young's double slit fringes that we actually see. Okay, so here we also want to define this quantity called visibility of the interference pattern, and this is the definition remains exactly the same as we did for time. So visibility is always I max minus I mean over I max plus I mean, and if we do find the maximum of this quantity, minimum of this quantity, we could very easily show that this is twice k1 k2 s rho 1 s rho 2 divided by this these two terms and then this degree of coherence. So that's the visibility, and now we can see if the intensity is coming from these two arms, that means k1 square s rho 1 k2 square s rho 2. That's a special case if these two are equal. That means there's an equal intensity coming from this hole and this hole, then we find that the visibility is simply equal to the degree of coherence. So if you make sure that the intensities coming from these two holes are equal, then whatever is the fringe visibility we see here, that is actually the degree of coherence between the field, degree of coherence between the field vibration at this point and at that point. Okay, so these are the basic ingredients for quantifying spatial correlation. Now just like in time where we saw that it is quite useful in actually classifying and quantifying the coherence in the temporal degree of freedom by going to the by looking at the correlation quantity in the frequency basis. So here we can do the same thing, and here the quantity in the conjugate basis of this cross-spectral density function, which quantifies the correlation in the space domain. This is related to this thing called angular correlation function, which is the correlation function in the spatial frequency domain. So this time also we'll find it useful that we do the quantification based on angular correlation function. So we can have the classification based on this, and so the case 1, the first case we often encounter is when there is no correlation between different spatial frequency components. So that means this angular correlation function, which is defined as an ensemble average of A star q1 A q2, this can be written as SQ1, some spectral density q1 and delta q1 minus q2. So this means if q1 is equal to q2, then only there is some contribution to a q1 k2. If q1 is not equal to q2, then this term is simply 0. So that this is what it means by frequencies having no correlation between different spatial frequency components. This is again very similar to what we had in the case of time, when we say there is no correlation between different frequency components. And just like in time, what we have here is that in this case we find, and this we discussed last time as well, that in this case the cross-spectral density function, this w rho 1 rho 2 z, because this constraint has to depend only on the delta rho, that is the difference in the spatial coordinate, and this side then becomes SQ to the I q dot delta rho dq2. So this is a nice Fourier transform relationship, and this is called the Wiener-Khinchin theorem. And the point here is that the correlation function depends only on delta rho for this case when there is no correlation between different spatial frequency components. Now what about intensity or spectral density? This S rho, which is simply W rho rho, and that's SQ dq rho. So this is just a constant. So for this case, when there is no correlation between different spatial frequency components, the intensity is constant or the spectral density is constant, and the correlation function depends on the spatial coordinates only through their difference. The second case is when there is perfect correlation between different spatial frequency components, and in this case the angular correlation function, which is again defined as this ensemble average quantity, we can just write this as A star q1 A q2. So this means the ensemble average doesn't make any difference. So this ensemble average is same as the quantity itself, because there is no randomness in the system. There is a perfect correlation between different spatial frequency components. So if there is no randomness, averages will yield the same value as the quantity itself. So in this case, the degree of coherence will always be 1, because since the frequencies are perfectly correlated, the fields will be correlated in spatial coordinates as well. And in this case, if we represent the field u rho z, that is this representation. This representation is now no longer symbolic. As we discussed, whenever we have the random variable, when we write its Fourier representation, it is mostly in the sense of it being symbolic. and we give it physical meaning only when we talk in terms of the correlation function. But when there is perfect correlation between different frequency components, then the field representation is no longer symbolic, it is the actual Fourier representation. This is same as also we saw that in the case of time as well. Again, we can have the most general case when there is partial correlation between different spatial frequency components, and of course in real life you never see this. This is always the case 3 that we see. These two cases are the extreme cases, and in real life we never ever see them, but it's like we see very close to it being case 1 or case 2, but it can never ever be, you know, the perfectly either this case or that case. But in most physical situation we try to approximate it to case 1 or case 2, and usually partial correlation studies are done when we go into the more detailed applications of spatial coherence. So here I'm just putting one example of an angular correlation function that shows partial correlation. So this is an example. This is called the Gaussian shell model source. As we can see in this case, this delta C kind of represents the correlation in the field between different spatial frequency components. And as we can see that when delta C tends to 0, this term is 0, then this will become a delta function, and this basically leads to case number 1. And when delta C is infinity, that means when the correlation is perfect, then it leads to case 2. So this is just a representative example of how we can capture kind of all these cases. So this is how we kind of classify spatial frequency correlation, and it is always good to, it's always kind of much easier to kind of handle correlation with this angular correlation function, and once we have it, then go back to calculating this cross spectral density function. Okay, so far we were quantifying correlation in time and space. Now we want to look at how these correlations actually propagate. So far we were just looking at what is the correlation, let's say at this point, and to find the correlation at this point, we look at the intensity at this point, and through the intensity measurement, we were trying to find out the correlation at this point. But now the question is, if we know the correlation, let's say at some z equal to 0, can we find the correlation at some other location? So that is the question. So now we know that the time evolution of electric fields is governed by the wave equation. So the question is, what governs the time evolution of the correlation function? So for a real field, since it follows wave equation, we can write it like this. So VRRT, this is a real field, and this follows the wave equation. This is the wave equation that we have written. One can very easily show that even a complex analytic signal corresponding to this real field also follows the wave equation. So this is VRT, this is the complex analytic signal, which is the positive frequency part of this real signal. This also follows this wave equation, that is del square VRT is 1 over c squared del to del t to VRT. Okay, so now that we have this, that the complex analytic part also follows the wave equation, we just want to now take the complex conjugate of this above equation, replace r by r1 and t by t1. So if we do that, here this derivative is with respect to r. So if it's r1, then it becomes del 1 square. This 1 just represents that this is with respect to r1. And we have, since we have taken the complex conjugate, so this is v star. So r becomes r1, t becomes t1, r becomes r1, t becomes t1, and this t just t1. So that is this is again the wave equation. This is just the playing with the variables. Now we multiply both sides of this equation by vr2 t2, and then take the ensemble average. So once we do that, so this is vr2 t2 that we have multiplied, and ensemble average vr2 t we have multiplied, and then taken the ensemble average. So this quantity also now follows this wave equation. Now what is this quantity? This is the cross correlation function gamma r1 t1 r2 t2. So that's the quantity. So we see that the cross correlation function actually follows a wave equation, but here this wave equation is only with respect to r1. The derivative is only with respect to r1, and this one is only with respect to t1. But we can as well have started from this point by taking the derivative with respect to r2 and t2, and in that case we would have gotten this equation instead, which is del square 2 this gamma and 1 over c square del 2 del t2 square and gamma. So both these equations, the gamma satisfies both these equations. So basically the cross correlation function, I mean the field satisfies one wave equation and the cross correlation function satisfies a set of two wave equations. And these are actually known as Wolf equation. These were derived by Emil Wolf, who was a faculty at the University of Rochester, and in fact he just passed away last year. So these equations are named after him. Now if it's a stationary and ergodic random process, then as we know that stationary random process, the correlation cross correlation function depends on the time coordinates, time variable only through the difference. So in that case, this equation basically becomes del 1 square gamma r1 r2 tau 1 over t square del tau gamma r1 r2 tau. And since this is the derivative with respect to r1, we can also have a second equation where we have the derivative with respect to r2. So these are the two equations that gamma r1 r2 tau, that is for the stationary ergodic process, that actually satisfies. We can take the Fourier transform of these two equations, and we can then find that the cross spectral density function, that is the correlation function in r1 r2, that follows this Helmholtz equation. Just like here, this is the wave equation, but if we take the individual frequency component of this field, then we see that those actually satisfy Helmholtz equation. Similarly, this is the cross correlation function, it satisfies wave equation. But when we take this cross spectral density function, which is the correlation at a given frequency between the two field points r1 r2, but at a given frequency, this basically satisfies the Helmholtz equation, and two of them, because this one is with respect to r1, this one is with respect to r2. So essentially the correlation function, just like the field, the correlation function also satisfies the wave equation. But in this case, they satisfy a set of two equations instead of just one. So, and by solving these differential equation, we can actually find out the correlation function at some other location if we know the correlation function at some initial location. Okay, so this is how we handle the propagation of correlation through differential equation. But let's next we also want to see how to handle propagation of correlation through an integral equation, through an integration, and in this context we will also discuss what's called the Vansittart-Zernike equation. Okay, so here we will actually get a little more particular. So in this case we want to study how the correlation from a spatial coherence of a primary source, how that propagates from, let's say, one point to another point. So this thing is, let's say, a primary source, and this is the origin, this is the primary source, and r1 prime, r2 prime, these are the 2 points. These are just the space variables on this primary source, and now we are after calculating the correlation function between the field vibration at these 2 points r1 r2 at some location from this source. Okay, so how do we go about it? So first we recognize that this field, this V r omega or u rho z, which is the field at a specific frequency, this satisfies the Helmholtz equation, that is del square k square V r omega. And if for finding the field here, we consider each point on this primary source to be a point source, and then the spherical waves, they actually come out of this point source, and then they finally reach this detection point. So here we consider this r1 prime to be a point source with amplitude V r1 omega, which is the amplitude of the source. So and then we will calculate the intensities. We will calculate the amplitude reaching this point due to this source. So if we have this r1 is a source at r1 prime with amplitude V tilde r1 omega, and let's say also consider d2 r1 prime, that's a tiny area at r1 prime, then the field amplitude reaching r1 from this point, that contribution can be written like this. Here we can see this e to the I k r1 by r1, that is the contribution. If we just take a unit amplitude source here, then these are the spherical waves. So if spherical wave, that's the solution e to the I k r1, and then r1 is the attenuation factor because this goes in a spherical manner. So e to the I k r1, where r1 is the distance from r1 prime to r1, this e to the I k r1 by r1, this is the quantity, this is the field amplitude reaching r1 from a source that is of unit amplitude at r1 prime. But since r1 prime the amplitude is v tilde r1 omega, then the total contribution will be v tilde r1 omega e to the I k r1 r1. And since we are also considering a tiny area d2 r1, then the contribution from that tiny area d2 r1 is simply by multiplying this quantity by d2 r1. Now this lambda 1k, this is just a geometric factor, we are also including here, because that will also, depending on what is the inclination of r1 with respect to r1 prime and so on, that will also decide what fraction of this field reaches there. Okay, so now, well, r1 is just the separation between r1 prime and r1. Okay, so now the total field at r1 due to the source is simply this integration, integrating the whole thing. So the total field at r1 is just v tilde r1 omega, this quantity, and this total field is just this quantity integrated over this whole source. And again, lambda 1k is a geometric factor. So similarly, if we take some other point r2, then the total field at r2 due to the source, due to the entire source, is again as a very similar integral. Here we are using this r2 prime as a separate variable, because we actually want to multiply this quantity. But this is same as this integral, except for this factor r2, which is the separation between this variable point that we have chosen r2 to r2 prime. Okay, so since the fields are related in this manner, so if we just multiply these two and take the ensemble average, then we have this quantity v star r1 omega, v r2 omega, and then this is just this ensemble average quantity, and we just put it all together. Now this one is the cross spectral density function at r1 involving r1 r2. This quantity is the cross spectral density function involving r1 prime, r2 prime, and this remainder is these are the remaining factors. And if we take the Fourier transform, we can also show that this cross spectral density function, then if we take the Fourier transform, this becomes the cross correlation function, and then we see that the cross correlation function at r1 r2 that's related with cross correlation function r1 prime, r2 prime in this manner. So this is just an integral way of representing how the correlations are correlated, how we can find the correlation at r1 prime, r2 prime. We can find the correlation at r1 r2 if we know the correlation at r1 prime, r2 prime, for both cross spectral density function and also for the cross correlation function. Okay, now we want to use this equation, this integral equation, for calculating the propagation of coherence function from a primary incoherent source. So now we are considering a source, this was for a generic source, but now we are considering a source that is completely incoherent. Now in this case, this is the general equation we have, and here and now I am using this for these geometric factors. We are using ik by 2 pi. This can be actually rigorously proven. You can find this in any optics book, but we are not doing that derivation here, but that these factors are ik by 2 pi. Now if the source is completely incoherent, which is what we are considering, we will have that this cross spectral density function is essentially this spectral density times the delta function. That means there is no correlation between field points. If it is not the same field point, there is just simply no correlation. So this is what it means by saying that this is completely incoherent. So spatially completely incoherent. So if you put this form for the cross spectral density function in here at the source point, then we get S r1 omega, this delta, we solve it, and then we have this form, that the cross spectral density function at r1 r2 now simply depends on the spectral density at the source. Here it was the cross spectral density at the source, but now for this completely incoherent sources, this is the form of the equation that we have, and this is called the von Sittard-Zernike theorem. So this says for a completely incoherent source, the spectral density of the source decides what will be the cross spectral density function of the field at some far away point. Now if the observation points, if the r1 r2 they are in the far field, so of course this equation is for when these points are separated by any distance, but then the point is when these two points are separated are kind of in the far field, that means far away from this the source, then we see that this r1 R1, we can approximate this R1 as this distance, which is just the perpendicular onto this line. So R1 can be approximated by this, and this thing is basically this whole thing, that is R1 minus this quantity, which is just the projection of R1 prime on this direction, and the unit vector in that direction is this S1. So R1 is basically the capital R1 is basically the small r1 minus R1 prime dot S1. Similarly, R2 is then R2 minus R1 prime dot S2. So this is for the when these R1 and R2 are in the far field. And in this case, then we can simply write this R1 R2 omega, we just replace R2 R1 by this quantity, and this is the form with this R2 R1 we can actually take out, and that's the form of the equation we have, and this is called the far field Van-Sittert-Zernike theorem. So this basically shows that a field, a source that is completely incoherent, that means if you take any 2 points that are even tiny bit separate, there is no correlation. Even if the field is coming from such a source, if you go to the far field or you go to some location away from the source, you do generate some correlation, and that we will see by some example. That here, when there was no correlation, now we do have this cross correlation function which is away from the source, which is non-zero even when these R1 R2 are not equal. So let's see that through one example. So this is the far field Van-Sittert-Zernike theorem. Again, we are looking at when the source is completely incoherent, and this time we look at in a specific example when it says the source is circular and spatially coherent and has a radius a, and the spectral density intensity just flat, that is just I naught over the radius a of the source. So just by doing simple math, we can show that this R1, since we are taking again the far field, so R1 R2 is just that's the far field approximation, and then we can show that this S1, that unit vector, is just x1 by R1, y1 by R1, z1 by R1, and since R1 is just z, we can write as x1 by z, y1 by z, and 1. Similarly for S2, the difference vector S2 minus S1 we can just write as some omega cosine phi, w cosine some psi, w cosine psi. Similarly, we can write R1 prime, that as some rho prime cosine theta, rho prime cosine sine theta, and so if we write S2 minus S1 dot R1 prime, which is the quantity we need here, we can write it like this. And if we then put this over here, this takes this form. If you just do the math, I'm not this one can actually just I'm not going through the details of it, but just showing all the math. So this they then can take this particular form where this V is this quantity, which is nothing but this Ka by Z times D, where D is the separation between the two observation points, is R1 R2. J1 is the Bessel function of the first kind and first order. Now we see that again we started with a source which was completely incoherent but had a finite size, and then we see that in the far field it has a finite coherence. That means now it is no longer the case that the correlation is 0 if R1 is not equal to R2, which is what the situation is right at the source. So it has, just by the propagation, now we see that the field has become coherent. And how much coherent? So that quantitative idea we can get by just noting that this first 0 of the Bessel function is at this V equal to 3.83 for this function, which corresponds to D equal to 3.83 Z by Ka. So this D equal to 3.83 Z by Ka, that's what we can call transverse coherence length. And this is then the radius, so pi d by, this is the diameter, so pi d by 2 square is the coherence area. A source which was completely incoherent, that means the coherence area or the transverse coherence length at the source was 0, but just by upon propagation we see that it has developed a finite coherent transverse coherence length and coherence area. So a primary incoherent source with 0 coherence area of the source generates finite coherence area in the far field. And this we see when we receive light from the sun. Sun is just a bunch of individual emitters, so the coherence area right at the sun's surface is actually 0. But when the sunlight comes to earth, it picks up coherence upon propagation, and if you actually do a Young's double slit experiment based on using sunlight, and if the two slits are separated by a couple microns, we will actually see interference fringes. The LED light, LED bulbs, they are also an example of such spatially incoherent sources, because they are also, to very good approximations, they are also this spatially incoherent sources. And in fact, for these such sources that are spatially incoherent or spatially partially coherent, there's a lot of application, especially in the imaging in the turbulent environment, and some of this application, if we have time, we'll actually go through in this course. So this is all for this lecture. Thank you so much.